Okay, sorry about the inconvenience. I would like to thank the organizer for inviting me, and actually also for scheduling my talk after Caterina's wonderful talk. Because of that, actually, I changed a bit my presentation. In fact, it is divided in two parts. The first one is it's a continuation, actually, of what Caterina has been saying. Seek this stuff from the modeling point of view, and starting from the work that we have done in collaboration. And then in the second part, I'll also touch something that she touched, something like collective migration from the modeling point of view. It's a work that is still in an embryonic state, but I thought that this would have been a good occasion to start discussing this issue and to present that. So, okay, so let's start from that. I mean, this is the picture, this is one of the pictures she showed, and we wanted to address the modeling of the importance of the nucleus in cell migration. And so the best model that we found in order to take into account of that is the cellular post model. We modified that in order to include, say, certain feature. For instance, the presence of the nucleus of the membrane, and other things like the minor things, like say motility, the motility that depends on several parameters and so on. And so this is the Hamiltonian that you have in the cellular post model that is made of an addition part, something that is related to the, say, shape of the geometry of the organs, let's say of the nucleus of the cell. And so on, the geometric feature of the thing, and then we use the cellular post model in order to see what happens when you embed this single cell in a.
Did you use a volume constraint for your
volume constraint? For the volume constraint, I thought the volume constraint here. Let's see. No, okay. For the volume constraint, here we are. For the volume constraint, we use this one. It's not a quadratic term. It's due to the fact that usually in cellular post model you might have that cells disappear because a finite energy is needed in order to shrink the cell to a point. Okay. So this one instead is more related to if you want, the stress compression experiments, which blows up when you squeeze the cell too much. So this is an asymptotic value when the area, for instance, of the cell is 0. So you prevent that.
As we have interrupted your talk anyway, feel free to ask also.
Yeah.
In a normal cellular pods model, you have a spin-like variable which is 0 or 1. Yeah. Now we have 4 values. How does this change the picture?
No. You have 0, 1. I mean, you have different. You might see this cell, this complex cell, as different cells. Okay.
So you basically 4 different pods models living on the same grid.
Yeah, if you want, or 4 cells. I mean, this is a cell that doesn't want to touch the membrane, for instance. Mm-hmm. Okay, so will stay always inside. Okay. Mm-hmm. Okay. Right. So we use that in a regular ECM and also in a random ECM, and you see here the 3-dimensional shape of the cell, and this is the nucleus. This is highlighted somewhat, and you see that it's squeezed. I don't say that this is more or less like that, but you know, there are some similarities. And what we find is that the speed, if you want, the speed of the cell depends strongly on the pore size. And there is an optimal pore size. This is typical of all the experiments that we did changing the parameters. So for pore sizes that were very small, then there is barely no motion because the nucleus is trapped into the network, and there is an optimal size which more or less is the size of the nucleus. This is the general outcome of this study, and then it decreases because the cell doesn't find enough, say, ropes to pull and make enough additions to move along. Okay, and with this we can also change two important features, which is the elasticity of the fibers and, of course, the nuclear elasticity. So this is the speed again. No, this is actually the aspect ratio when the nucleus is rigid, and when this is when it's more elastic, if you want. And regarding the speed, you can look at this graph here. This is the velocity. Take a pore size, and you have the this is the elastic nucleus, and this is the rigid nucleus. And you see that when you have an elastic nucleus, the speed is much faster because, of course, the nucleus is squeezable, and the cell is able to pass through narrow pores. Okay, but of course, when the
trying to connect what you're remarking on here with the original model.
Yeah.
So could you help us by perhaps going back to the model and identifying those parts that actually connect the fiber, nucleus elasticity? For some of us, we've not met this model ever before.
Okay, yeah, sure. Here it's a bit different. It's a bit difficult from this picture. In this cellular post model, there are several ingredients. One is the cell with the organelles. The main organelle is nucleus, okay, and and the other one is the outside of the cell, which is made of two things. One is, say, if you want, the physiological fluid, and the other one is the fiber. So if you want, in the model, you have say the fibers that let's do it in the aligned way, okay, that can move, and you have, say, some energy that is needed in order to move that. Okay, this is the, if you want, the preferred configuration, stress-free configuration. If you want to, if the cell is here, and this, in order to pass through this region, it has to, say, deform this network. You have to spend some energy, and you put that into this this Hamiltonian here. The Hamiltonian, you can call it Hamiltonian, you can call it generalized energy. In the other one, on the other point of view, also the nucleus, looking at it from the continuum mechanical point of view, needs some energy in order to be squeezed, and this is here. Okay.
So I guess just again, the Potts model is historically a spin model, so I'm still not understanding what the basic kinematic parameters are here. Are we attaching spin variable to these cells, or what are we attaching to these cells?
What do you mean with the attention?
What is the kinematic descriptor? Forget the energy. What is the field that's being evolved here?
It's the energy. You are trying to minimize the energy. Probably I didn't understand the question. Probably we can discuss that later.
Yeah, sure. There's no spin. Yes, I'm trying to understand what the basic kinematic descriptor
just mechanical energy.
It's a mechanical energy, and you are trying to. There are fluctuations. You are trying to minimize this energy. Okay. So let's see. Okay, this is one feature I already discussed. We also did some experiments in 2D, numerical experiments in 2D, and we also find the same thing in the sense that you have again the optimal, say, number of fibers in order to have, say, the highest speed. Again, because if there are not enough fibers, there is not enough addition, and then a possibility of pulling. If there is too much, then the cell sticks to the matrix, expands a lot in order, in terms of energy, in order to move. And this can be related with these experiments by Politecnico and his group, in which they found also this biphasic behavior. So this is what we did. Then again, with the cellular pods, we try to work in a microchannel, say, setup by having, say, 3 channels. One is larger than the cell dimension, typical dimension. One is larger than the nucleus dimension, is smaller than the cell dimension, and one is smaller than the nucleus dimension. And see how moving by chemotaxis is in this direction. So we added a chemotactic term, and how this can, how is the speed related to this geometric feature of the microchannels. And this is the case in which the nucleus is stiff, and so you see that in this case, this nucleus, though the cell would like to penetrate into the microchannel, and you see the extension of the cytoplasm, then the nucleus is lagging behind, and so will not be able to penetrate into it. And this is, unfortunately, I cannot show you the movie, but there are some movies in which, with the microchannel device, you have this same feature here. But if you allow some elasticity of the nucleus, then the nucleus again is highlighted here. The nucleus is squeezing, and of course, with some difficulty with respect to that one, the cell can squeeze through the also through the narrowest microchannel. Okay, and so again, we have this average velocity in terms of the pore size. We find the same thing as before. There are two things to notice here. The first one is that for large pore sizes, the elasticity of the nucleus is not important, as you expect, because there is no influence of the size of the nucleus and then of its elasticity. Instead, when the pore size is small, then there is some dependence on the elasticity. Of course, the softer nucleus go faster than the rigid nucleus. And these dots here relate to the experiments by Katerina Wolf that she showed before. Okay, these dots here. Okay, which are more or less this. Yeah.
Does your nucleus conserve volume?
Yeah. Well, the nucleus conserve volume. Again, in cellular post model, you don't have a constraint on nuclear conservation. Okay, but in order to move to say change the volume, you have a penalty term. You pay in terms of energy. Okay, so it's not incompressible in the mechanical terms, but you spend something. Okay, so and this has to do also with this experiment that probably I think Katerina showed a similar graph like this one, but this is from her, in which you see that the velocity is the speed of the cell is plotted as a function of the pore section of these networks of the bovine and reptile networks, and you find that below a certain cross section there is no motion, like for instance in cellular pods, and then more or less it grows, I would say, if you want linearly, if you want something like that. Okay, so we try to answer this question. Well, actually, if in the microchannel setup, it might be possible to find a relationship based on continuum mechanics. So I'm now switching modeling framework in order to see when the cell will go through and where the cell will not go through. Okay, because what you observe is that in order to squeeze this nucleus into the microchannel, you have to spend some energy, and this energy is given to the cell by the pulling force, by the traction force that the cell is able to exert. So we did that in several configurations for the nucleus, in the ellipsoid, and when it deforms like a cigar shape, it doesn't change much from the output point of view. And of course, the other feature is that to describe how the cell exerts traction on, say, the wall of the microchannel, and basically, say, most of the traction is on, say, on the tip of the cell, on the rear of the cell. This is not the case in the microchannel. So we assume several forms of these forces that are acting on the wall of the microchannel, say this is the force on here that is pulling the nucleus inside. So the general idea is the following. As I said before, in order to squeeze the nucleus through these narrow holes, you have to do some work. So, and the work done by the traction forces of the cell need to be larger than the energy required to squeeze the nucleus inside the cell. Okay? I don't want to enter into detail. You do some basic continuum mechanics, and then at the end of the story you find some criteria. And the criteria is the following. Let's focus on one. Okay, the ellipsoid, this one. And then you see an elastic nucleus with an ellipsoid. You find that this number, this is a dimensionless number, need to be larger than some other quantity in order to have the penetration into the microchannel. Now, this number here is what? Is a ratio between something that has to do with the forces. This is the, say, how the cell is able to exert traction on the number of addition points, of focal addition points, the number of bonds that the cell is able to do on the wall. And here at the denominator you have the stiffness of the nucleus. So it measures, in some sense, the first force, the active force of the cell versus the nucleus stiffness. Okay, and this ratio is to be larger than a certain value that depends on what? This Rp is the ratio of the radius of the pore with respect to the radius of the nucleus. Okay, so it's not very easy to see, but graphically is much easier. Okay, it says the following. Again, focus on one of these. There is a region in this space of these two parameters. This is that ratio, force with respect to stiffness, and the ratio of the pore with respect to the nucleus. And in this region, there is no way the cell can go through the microchannel. Okay? Which means that, for instance, if you have a given cell with some given characteristics, if the pore of the nucleus is too small, then it will not go through, and if the pore is large enough, then the cell will be able to penetrate. Otherwise, if you look in this direction, if you have a given, say, network, a given size of the microchannel, then if this G increases, then you are again able, the cell is again able to pass through the microchannel. Which means, by the way, there are two ways that this can happen. Of course, this G can increase because the denominator becomes smaller, which means that the nucleus becomes more elastic, or the forces are larger. So in this way, you can indiscriminate situation in which you might have two different clones, one with the, say, stiff nucleus and one with an elastic nucleus. And the elastic nucleus, the cell with the elastic nucleus will pass through and the other one will not. Okay, the following step is to use that information in a microscopic model. Say, now we are, say, jumping from the behavior of the single cell to the behavior of, say, an ensemble of cells, of a tissue, and to embed that information in order to have, to be able to describe situation in which, say, basal membrane, for instance, segregate some cells that are growing. I don't know, I'm thinking about the islet of Lagrange. You have this membrane, you have the tumor that is growing, but it's still constrained into this bag, okay? The membrane is a porous material, and as a porous material, the cell could pass through, but it's a very tight network, and so it will not pass through this network. Usually, what is done in this type of model is to, okay, let me just describe a bit this equation. This is just the mass balance equation for the cell. This is, you can forget about that, but this is just the mass balance equation for the extracellular matrix. I will not consider that one in the simulation that I will show. And this is, in some sense, the force balance. This is the stress related to cell compression, if you want, to the behavior of the cell, and this is the interaction force of the cell with respect to the matrix. Okay, and usually these terms here is taken to be proportional to the velocity, to the relative velocity of the cell with respect to the extracellular matrix. Okay, so the question are, okay, from what we learned, this interaction force depends on a lot of things. It depends on the pore size, depends on the nucleus elasticity, on the fiber elasticity, and usually it might have this bimodal behavior because there is this optimal velocity you can experience. Okay. So at the end of the story, in order to take into account of these experiments here, what you have that is this velocity of the cell is proportional to something like, say, that has to do with the stress of the ensemble of cells through some coefficient that is linearly related to the size, the, say, cross-section of the network minus the minimal cross-section, this A0, that allow cell motion. Otherwise, it's 0. Okay, so this is the basic feature. It says this is the positive part. So it says if AM, the size of the pore size of the network is smaller than A0, I don't have any flow. If otherwise this is larger than this one, then I have some relative flow, and the cell can move into the extracellular network. Okay, forget about it. Yeah, and you can embed into. Well, no, I have to go to explain this one. Oh. The question is that in the experiments done by Caterina, that A0 of course is constant, but what we learn is that A0, the minimal pore size in order to allow, say, penetration, is not a constant. But actually, that A0 depends on a lot of things. Depends on the nucleus size, of course, because, say, cell with smaller nucleus will pass through. Depends on their elasticity, okay? Of course, because we have shown that elastic nuclei will go through, and depends on other things like cell adhesion, active traction, and so on. So that A0 is related. That A0 is related actually through to this G that you have seen before, through which is the trace of the traction, the tensor, the stress tensor, through a curve that is very similar to the one that we showed before. Actually, is deduced from this one. Okay, so you have some criterion from that A0. So it's a complex model, but at the end of the story, it makes the jobs that you want, in the sense that assume that you have a situation. This is just a 1D dumb simulation in which you have, say, a region in which you have, say, a volume ratio of extracellular matrix to 20%, occupied by ECM to the 20%, and then after that you have a thicker region, and you have a population that is growing in this region, then it's growing. Then when it arrives in this situation in which the network is more dense, then you will just stop, because it cannot invade this region here, because of course there is no when say metalloproteinases is inhibited. Okay, instead, and this is if you lower this threshold, this dense region to say 0.25, because of the coefficient, how the coefficients are in the model, then the cell can penetrate to also this region here. So it depends. It depends on the morphology of the network, and this is in 2D is the same thing. Actually, here there are two populations. You don't see the other one, but there is a population of normal cells that is filling all this region below this stripe here, and also above this stripe This is just a region with a dense, say, extracellular matrix. This is a sort of a tumor that is growing at the expenses of the normal tissue, but assuming that the nucleus, say, is stiff, then it cannot penetrate this region here and will stay below, say, this membrane. But if the volume ratio of the membrane is not, say, thick enough, the membrane is not thick enough, then it will invade also the outside of this thick region. And here is what happens instead when you lower the stiffness of the nucleus. I did it in 1D, not in 1D. This is just one section, and this is the, say, normal population. This is the tumor population, and the normal population you see doesn't go to the other side, but the tumor population with the softer nucleus is able to invade, say, the membrane, the thick region, and then the outside of this region. Okay, so, and then of course now you can play with it and say do another simulation in which you have a region with thick extracellular matrix, very thick, not so thick, and so on, and you have the structure of the extracellular matrix determines where the tumor will pass or not pass. Okay, so this ends the first part. Now let's go to the trying to make a model that has to do with collective migration. So what is the problem here that we wanted to address? There are several situations in biology in which there is an ensemble of cells with some differentiated cells, and you need to take into account of their different behavior. And the behavior of some cells is like single entities in an in a population of other cells that behave more or less amorphously, that just follows. These are some examples. This is the zebrafish in the embryonic development. At some points you have the formation, the differentiation from this cloud of cells of some germs that will make some rosettes, what they are called rosette, around them that detach from this, and this forms the lateral line of the zebrafish. So you have a migration of a population of cells, a collective migration, but at some points, because of some, chemical mechanism, some differentiate, and you need to, and then you form some, say, cluster of cells around them. But there are other things. Unfortunately, I cannot show you this movie here. These are some cells that are called MLP29. We were working on that several years ago, and they are activated by AGF, by hepatocyte growth factor. And when they are activated, the cells that are at the border just tend to form this star-like shape. They try to elongate, more or less like the what was that? The clone that you show, the breast cancer that you show, the breast cancer that Caterina showed. That is, the cell at the periphery move. They become very motile. They tend to say, extend radially, and they pull the other cells with them. But there are other examples. Okay, this is the collective migration. This is a picture by Caterina Wolf and Peter Frieder, with, say, some leader cells and some follower, or you have, say, tip cells and stalk cells in angiogenesis and so on. You have these situations, and we want to see if we can do something from the modeling point of view. Okay, so what I'm now presenting is work essentially by Anna Chiara Colombi, Marco Shan, Andrea Tosin, and in part myself. One of the idea that we had is to use measures to describe this kind of things, because measure can be, of course, delta function, say discrete cells, or can be just absolutely continuous. And we can, say, merge the two things. That is, this measure is evolving through some velocity, okay, some flux, in which you can, say, discriminate one that is related, say, to chemotaxis, for instance, or some taxis phenomena, and one that is related to the interaction between the cells. Say cadering the interaction, and or even integrin if you want, but in this case it's just cell-cell interaction. So and this takes the form of an integral with a kernel, with an addition kernel. So in some sense the cell senses, as a sensing radius, senses the environment. This is not very different from what, for instance, Jonathan Scherrer, Kevin Pinter have been doing, also Hart, I guess you will talk about that. Yep. So the model at the end of the story becomes very non-local for this. So this is just, you get this transport, say, sort of mass balance equation from Reynolds theorem, from transport theorem, with this shape of the velocity. So this is a toy model. And that becomes very familiar in the case of, say, fully discrete situation, in the sense that cells are just, if you want, this measure is just a sum of delta functions. So you have this dumb ODEs, where the velocity is given by, say, a directional part and an interaction part. And also in the fully continuous, the situation also becomes something very, very easy, in the sense it's just the mass balance equation and say a velocity with this non-local term. But the interesting situation is when you have a hybrid situation. This is what we want to address, because in this case, when you have, say, that part of the measure is delta function and part of the measure is a continuous, is absolutely continuous, then you have the merging of, say, some ODEs, n ODEs describing the n, say, cells that are behaving in a discrete fashion, differentiated cell if you want, and the other one which is describing, say, the plethora, the ensemble of cells that are just not activated, not differentiated in my term. And in the velocity term, you can take in the velocity term, which is similar for them, you can discriminate the interaction between, say, discrete or discrete and continuous, and the other one with the continuous and so on. Coming to this interaction kernel, there is a sensing radius, as I told you, that is the cell, say, explore a certain environment with certain radius. If you want, it's the maximum extension of the philopodia. And there is also another radius, which is the, say, repulsion radius, so that the cells don't, say, overlap. And one might have also isotropic interaction if the cell senses all around its environment, or anisotropic interaction in which this the support of this kernel is just a certain region, for instance, ahead of the cell. Okay, so the cell is sensing only what happens in this, I don't know what, semicircle, hemisphere, for instance. And this is what you get. This is just some preliminary results. This is just an ensemble of cells that at some points one single cell differentiate and chemotactically wants to move toward the right, but because of the interaction, adhesive interaction with the continuum, and also the continuum, of course, of the cells want to stay attached, want to stay compact, then it pulls on it and you make the strand. And this strand is only related to the fact that this one, this little point, wants to move to the right. Okay, so depending on the parameter, of course, as you can understand, for instance, on the strength of the chemotactic force, on other things, you might have that this will stop or this will just detach part of the cells from the whole. Yeah.
Very interesting. And may I ask, does your nucleus deform?
No, these are just These are here. The nucleus is not important.
Okay.
Okay, so it's just a single entity, or say an ensemble cell, and you don't discriminate the suborgan, if you.
Thank you.
Okay, and this can become more complex. This is just again starting from a spheroid, if you want, and there are 3 cells. You have the formation of these 3 spikes, and you can have different features according to the parameters, if you want. Okay. I don't know if you can find some similarities with the movies on the breast carcinoma.
Question?
Yeah.
What did the dots represent, for example?
The dots represent. In fact, I was just going to that. The dots represent the position of the delta function, the center of mass. But you have to take into account that this is not the point, because there is an area around it which is related to the radius that the cell doesn't want to, the minimal radius of, say, for instance, the nucleus, the volume of the cell, and then there is a sensing radius. So this is what this little circle here is what I call the I don't remember, RA is attraction, RN. This is RN, which is the radius more or less of the repulsion thing. So it's not detaching in some sense from this, it's just leading this one. Okay, what is the problem with this model? The problem is that using measures, in some sense, you are too restricted to the fact that, for instance, the integral has to be constant. Instead, in several situations, you want to do 2 things. One is to transfer mass that is to differentiate from continuous to discrete and vice versa. And the other thing, of course, that you want to grow. The cell, the ensemble of cells, the spheroid need to grow, and that is to change mass. And you cannot do that with this kind of model. On the other hand, you don't need that, in the sense that at the end of the story, we are replacing a discrete entity with some, say, point. We are describing it as a point, thinking that on this point there is a cell with a finite size. So in a second approach, what we use that is to describe the mass as localized mass and distributed mass. The localized mass is some given shape. So if you take a cell like this, you can assume that this is more or less as we call it bubble function, a shape function, if you want, in numerical terms. So whenever we replace a part of a continuum with one single entity, we are taking out of our distributed mass some sort of Bell function. Bell function, bubble function, whatever. We call it bubble function in order to say, because Bell function is not just the Bell kernel. Shape function has some different meaning in numerical analysis. So it's a bubble function. So the idea is the following. At some point, you start with say n localized cells, n localized cells, and you want to decrease the number of cells by a certain amount at some instant, and you can increase the number of cells by a certain amount by differentiation. Okay, taking that mass where? From the continuous. So we are losing some points, if you want, some differentiated cells, which becomes continuous. M is the mass contained in a single cell, or we are differentiating continuous, the continuous distribution in single Bell function, single bubble function. Okay, so we are increasing the number of points that are evolving, and we are changing the mass. So these terms here in blue are the ones that are related to the transition from localized cells to distributed, is on the Dave differentiation, and this has to do with the transition from distributed to the localized. Okay, and the modeling is very similar to the one before. That is, you can write down, say, for the distributed cell, a mass balance equation. But the difference here is that you can allow for some growth term on the right-hand side. That is, the distributed mass can grow, like the spheroids. And you have some ODEs for the describing the center of mass of these bubble functions. Okay. Well, the velocities here are similar as before. You can see. Well, in this particular case, we assume that the directed part of the velocity, say the chemotactic part, is only affecting the discrete entities. So this is Dm is the discrete entities. Then this is the interaction between discrete entities. This is the interaction of the discrete entities with the continuous one. And this is the velocity of the continuous. Is the interaction of the continuous with respect to the discrete and continuous with respect to the continuous. So you can take into account of all the interactions. But the structure is still very similar to that. But in principle, I'm confident that you can expand this basic thing to other more complex model of cell migration. Again, I cannot show you the movie, but this is one example. We have say a spheroid. At some point, you have the formation of some metastasis. This points here at the border that will chemotactically move toward the say the border of the square and pulling, say, with them some strands in some sense. Okay, this is what this can do, and this is the other experiments in which you have, say, an ensemble of discrete cells at some that are moving toward the right. At some point, some cells differentiate, and this induces around some de-differentiation of the cells that just cluster around, becomes continuous in some sense, and this will just occur 2 or 3 times, and then after that, this zebrafish primordium, this primordium will just start moving and forming other rosettes. Okay. So that's it. Well, I also have lost this picture here of Anna Chiara. So this is the guys that were working more or less in the I don't know. This is very strange. In the transfer, Anna Chiara disappeared. Okay. So this is the group.
The ghost scientist.
This is the mystery of informatics. Okay. Hey, thanks for your attention.
Two questions. Can you say anything analytical about the solutions of the PDs, the last PDs that you have shown?
No, we didn't do anything analytical on that. You mean because I showed this one?
Yeah.
No, on this one I cannot say anything. I don't expect many problems from that. Of course, most of the behavior depends on the interaction kernels that you put in here. Okay, but in principle, non-locality might give you, might smoothen out some solution. And then, of course, you don't have, even, well, let's do that. Assume that here I have some Keller-Seeger stuff, okay, which I don't. It's just, so that is, this chemotactic term is related to the density of the cells, okay, so that you have clustering. In principle, these terms here, this non-local term should smooth out the solution. This is what I expect. Because, and then of course, the fact that there is a repulsion radius will also help.
And how do you solve these models?
This model is solved by finite volumes. I mean, this part here. Because you, well, actually, when you have gamma, you don't have this problem, but when you have 0 here, you want to control the volumes, volume conservation. And so binary volume is the best, right, best, to my knowledge.
Time for a coffee break. Thank you very much again. So we reconvene at 11:30.